All right, so what we're doing today is we're going to discuss gravitation. Okay, you know gravitation, right? What is gravitation? In chapter 2, you learn about gravitational acceleration. So what is that value? Gravitational acceleration. 9.8, and we use this symbol G to indicate that's gravitational acceleration, right? So technically, your G value here, that stands for free fall acceleration. So the definition of free fall acceleration and gravitational acceleration is a little bit different. How different? Which we're going to talk about it in just in a few minutes. So gravitational acceleration, this G is free fall acceleration, and gravitational acceleration, we will just use A sub G to indicate that's gravitational acceleration. You'll find out most of the time, you can approximate the gravitational acceleration to be equal to free fall acceleration. What is free fall acceleration? Free fall is the amount of force to prevent it from falling down. So this is called free fall acceleration, which is 9.8. And gravitational acceleration, that will be when you set up the net force equal to ma, and that will be your A here. So this is gravitational acceleration. So what is gravitational gravitation? If you have mass 1, if you have mass 2, they all come with the mass. Okay. What we found is that these two mass particles, they interact with each other. How do they interact with each other? They interact in a way that they exert forces on one another. So in other words, when particle 1 sees particle 2, it's going to experience a force. And that force, we found that the force magnitude, which is just the magnitude, so it's equal to a constant, which we call a gravitational constant, and then times mass of particle 1, mass of particle 2, and then divided by the distance between them squared. So let's say the distance between them from center to center, that's called R. So that will be R squared. So this is the magnitude of gravitational force, in which case any two particles, they're going to exert forces on one another. And that force is called the gravitational force. It has a magnitude of G, N1, N2 over R squared. So what is that G value? The G value is a constant. We call it a gravitational constant. So G has this magnitude of 6.67 times 10 to the negative 11, and the unit is Newton. Okay, and then times meter squared over kilogram squared. So that's gravitational constant. And so you can see that the magnitude only depends on the separation between the two particles and also the mass of each particle. So G, M1, M2, and then over R squared. Force is a vector. So we know that the magnitude has Gmn over R squared. What about its direction? What is the directions of the force? To answer that question, we found that gravitational force is considered as an attractive force. What does that mean when a force is attractive? It means that when two particles see each other, it has a tendency to move toward each other. This is called attraction, right? Now, in 212, you're going to learn that forces may not always be attractive. They may be repulsive. Like two electrons, they carry the same signs of charge. When you place two electrons together, their interaction is repulsive. They want to run away from each other. But then when you have a positive charge and negative charge, they want to move toward each other, and that's considered attractive. Now, in this case, gravitational force is always attractive, which means that any two particles, as long as they have a mass, they are trying to congregate each other. So in other words, they have a tendency to move toward each other. So in that case, let's say this is particle 1, this is particle 2. What is the directions of F12? F12, that's in vector form. So that will have, this reads the force acting on particle 1 due to the presence of particle 2. So F12, so 1 is the one that, what are the forces acting on particle 1? Okay, so you have F12. So this particle 1 experiences a force coming from particle 2. So in that case, when particle 1 sees particle 2, which direction would that be? When particle 1 sees particle 2, the force being attractive, what will be the directions of F12? It will be toward that particle, right? Yes, okay, so the direction, so you would specify your F12, your F1, so that's it, this is your F12. So you say your F12 in vector form, we have this magnitude, which is F12, and then it is rightward, so you will use F12, which is a magnitude, and then I hat, indicate that's a rightward force. Now, what about the force acting on particle 2 due to the presence of particle 1? So, this is particle 2. When particle 2 sees particle 1, it will have a tendency to move toward particle 1 because it is attractive. So, you will have F21. So, now the force is called F21. Your F21 will be in that direction, okay, because it's attractive, okay? Are we all paying attention to the new material? Yeah, okay. So, now, what is the magnitude of F21? If you look at this expression, F21 will have a magnitude, again, same thing, G, N1, N2, and the separation between them squared. So F12 and F21, they have exactly the same magnitude, but they are pointing in the opposite direction. F12 is pointing rightward, but F21 is pointing leftward, okay? So in fact, they form a the force pair for the Newton's third law. So you can see that for F21, you have the same magnitude F12, so I'm just going to use F12, and the direction is opposite in the opposite direction, so it's negative and then I hat. Okay, so this indicates that any forces, any two particles, they're going to interact, and their interaction is, it means that there's a force between them, and that force is called the gravitational force, and has this magnitude, and then pointing in the toward the other objects. Well, if you're talking about the system, but usually we don't find the net force acting on the system. We're actually finding the net force acting on particle 1. So you have to identify which object that you want to find the net force on. Okay. Now, if you're talking about the net force within the system, yes, when you add them together, they cancel each other, right? But then when you so within that system, if you have this particle, then your task is to find out how many forces acting on this particle. What forces acting on this particle is irrelevant to what forces acting on this particle. Okay, so that's why how you write this force, how you represent this force is important, because you can have a third particle. Let's say I have a third particle right here, and we know that by the Newton's law of gravitation, these two are going to interact with each other. These two are going to interact with each other, but do I care how these two interact with each other if I want to find the net force acting on particle 1? No, we don't care. Okay? It is how many forces acting on particle 1 that is important. It doesn't really matter how the other particle interact with each other. It's irrelevant to how particle 1 experience. Okay? All right. So that basically tells you that you have the formula. This is just a magnitude. And how to determine the direction. Common sense, attractive, which means that when this particle sees that, it will be pointing in that direction. When this particle sees that particle, it will pointing toward this particle's direction. Okay, and this is why we call that force is attractive. Okay, so take for example, now we have the Earth, and Earth is basically you can consider not the Earth, but we can consider that you have a spherical shell, which means that it's empty inside. You just have a thin mass that is evenly distributed along the surface of the sphere. So let's say you have a sphere, okay, spherical shell, and that has a mass. Let's say that the total mass of this shell, let's say capital M. Now let's say you have a particle that's so this is the center of the sphere. Let's say this is distance r. So you have a tiny little mass right here. It doesn't really have to be tiny, but let's just say you have an object. So now we have two particle systems. One is spherical shell, and one is a particle that has a mass m. How do we find the gravitational gravitational force exerting on this particle? That is actually on the surface of the spherical shell. What is the force acting on this particle? What is the magnitude? Yeah. The center of gravity.
Mass of the spherical shell, and that this is being the center of mass of particle 1 and the spherical shell.
So in other words, you will still use F, that's equal to G, M1, that's your M, right? And then M2, that's the mass on this spherical shell, right? And then over, what is the distance between them? The distance will be from the center of the shell to where the particle is resides, right? So it's R squared. So you utilize this because implicitly you're thinking this big spherical shell as and you're using the center as if all the mass was were actually concentrated at this point, right? So this equation translates to this. This is the total mass of the shell, and this is where the little m here, and this is the R here. So what you just use is what we call the shell theorem, which means that when you have a spherical shell, when the mass is evenly distributed along the surface of the shell, you can consider that the mass will concentrate as if the mass will concentrate at the center of the sphere, and then you can utilize this equation to calculate the gravitational force experienced by this two particle system. Okay, so in other words, instead of thinking of it as an extended shell, you now thinking of it as a like two particle system. One is a tiny little particle, and one is that as if all the masses will concentrate at the center of the spherical shell. Okay, so you will have that, and the directions, of course. Again, this particle experiences gravitational force that's pointing downward because it is gravitational force. It's attractive. Now, this particle, this shell, also experiences gravitational force as well from that little particle, and it will be toward that particles. Okay, so this is when you have a particle that resides outside the spherical shell, experience gravitational force with this magnitude gmm over r squared. So everything is as usual, nothing other ordinary, because you're just basically thinking of this as a central mass. So you all these masses will concentrate at that point. Okay, so that's your capital M. What about if you have a particle? We move this particle inside the spherical shell. What kind of forces? What is the gravitational force experienced by this particle? Yes? Is it?
Or will be the same equation, just that R will be different. Because when you kind of cancel out the force.
I don't know. What's your take? What is the gravitational force experienced by this particle if that's inside a spherical shell? The answer is it experiences no gravitational force whatsoever, because the key word here is that all this particle, if you divide this particle on the spherical shell, and then so you have this tiny little mass here, you have this tiny little mass here, and then so you basically form, there's an interaction, so there are forces pointing in all directions. So when you have forces, acting on this particle, and that's pointing in all directions, they cancel each other. So the net force acting on this particle inside the shell, you'll find that to be 0, which means that even though this one has a mass, the spherical shell also has a mass, but when you place that massy object inside that spherical shell, all the forces acting on this particle gets cancelled. So the net result is that it experiences no gravitational force inside the spherical shell. Okay, and this actually sparked a lot of scientific writing. I mean, science fictions. We have spherical shell, no gravitational force acting on it, and then so I think there are some novels, scientific fiction that deal with this kind of subject. But this is what we call the shell theorem. If the particle is outside the shell, you treat this shell as a particle, another particle. If the particle is inside the shell, then it experiences no gravitational force. And you can just use calculus to integrate all the forces acting on this particle, and you'll find that it just cancel each other. Okay. So we mentioned about when you divide this this shell into like tiny little particles, and each part is going to interact and add up all the forces. So let's take a simpler case. Let's say we have a few particles. And then how are they related? How are they interact with each other? So in order to sum up the net forces acting on one particular particle, this is basically what we do. This is the standard approach. That we just find out all the forces acting on that particle, and we just add them together. And after we add them together, so let's say if we have within the system, let me draw X and Y. So let's say you have particle 1, you have particle 2, you have particle 3, and you have particle 4. So let's say you have a 4-particle system. Take for example, we know that they are going to interact with each other. So there is a gravitational force acting on one another. This particle 1, how many forces act on particle 1? How many turns? You have 4 particles. How many forces acting on this particle 1? Yes? There will be 3. Let's see. All right, so let's see. When particle 1, so now our task is to find net force acting on particle 1. And I think, so we call that F1 nets. And we identify that there should be 3 turns. So how many forces acting on particle 1? When particle 1 sees particle 2, it has a tendency to move toward or away. Towards, right? So particle 1 sees particle 2 is going upwards. So so this is F12 at 2021. That will be 1, 2. When particle 1 sees particle 2, so that's your F12. When particle 1 sees particle 3, which direction would it go? Rightwards, because attractive. So this is F13. So we're pointing in that direction. What about your particle 4? When particle 1 sees particle 4, diagonal, okay? So let's draw the line connecting these 2 particles. So this will be the directions of F14. So altogether, are there any terms that are acting on particle 1 besides these 3? No, right? Because you also find the net force acting on particle 1. There are interactions between these other particles, but we don't care. We only care about how many forces acting on particle 1. So you will have F12 vector plus F13 vector and plus F14 vector. So what we're using here is what we call the principle of superposition. Basically, it is the net effect can be found by summing the individual effects. Okay, so in other words, you want to do a vector sum. Again, I'm talking about vector sum, not algebraic sum. When I say algebraic, which means that let's say this one has a magnitude of 4, this one has a magnitude of 3. Those are magnitude. You don't just add 3 plus 4. That will be incorrect unless they are in the same direction. Most of the time, they are not in the same direction, so you have to actually draw, like in this tape, this coordinate shows this one pointing upward, so it is in the j hat. This one pointing rightward, that's I hat. This one is diagonal, which means that you have to resolve this vector into the x and y in order to find the x component and y component. Okay, so it's not as simple as just adding together. No, it's a vector sum. So we have F12 vector plus F13 vector plus F14. Those are the vectors. Those are the forces contributed to, that's acting on particle 1. Okay, so we can just say that to generalize this, that will be summation of F1, and then you have so F1, and then we use I, and I start from 2 to n. So you don't have F11 because it does not self-interact. So you have F12, F13, F14, and so forth. Okay? Any questions so far? So we utilize the principle of superposition. We do a vector sum in order to find the net effect on particle 1. You can also find the net force acting on particle 4. If you want to find the net force acting on particle 4, then you have F41, F42, F43. You don't have F44. Okay, so that's basically how you would do it. And once you know that, then let's say, what is your F12? So your F12 will have a magnitude of capital G, mass M1, mass M2, and then the distance between them. So the distance between them, I'm just going to call that R12. So you have your R12, and do not forget to square it. So you square it. This just gives you a magnitude. It does not give you a direction. So what will be the direction? So F12 is this. So you will draw, use a vector sign. It is pointing upward, so it is j hat. Okay? What about your F13? Your F13, magnitude-wise, will be G, M1, M3, and then the distance between them. The distance between them, I'm going to call that R13. So you have your R13, you square it. And what is its direction? I hat. So that will vector sign and then I hat. Okay? Now, so F12, F13 are easy because they're along the axis. What about your F14? So hold on. F14 with the magnitude, that will be your G, M1, M4, and then the distance between them. So I'm just going to call that R14. So it's R14 squared. So this is the magnitude. How do I resolve this into the x and y component? To resolve it, you have to have an angle. So let's say this angle, we call that theta. Okay? So this is your vector, and then you have this. This is your y component. This is your y component, and this is your x component. So in that case, your F14, I'm just going to, so the magnitude is this. So the magnitude times cosine theta. This is adjacent. This is adjacent to the angle. So that's your cosine theta, and that's pointing rightward. So you use a positive. So cosine theta I hat, and this one is pointing upwards, and this is opposite the angle. So that will be sine theta j hat. Okay? So this is how you express F14. You have to resolve it into an x and y component. First of all, you've calculated the magnitude. After you have the magnitude, then you have to go by the diagram to see what is your x component, what is your y component. Because you're using small angle notation, you have to manually put a negative sign if it is pointing downward or leftward. Okay? In this particular case, because it's pointing, it is in the first quadrant, both are positive. So we can just safely use cosine theta I hat and plus sine theta j hat. Okay? Any questions so far? Yes?
When you're resolving into vectors, is it two separate equations, like cosine?
Yeah, so
And then you do a separate one for the y?
yeah, you do that, but I just combine them because this, when you multiply this, that gives you F1 for x component, and this multiplied by this gives you the y component. So I'm just, because they have the common factor of the magnitude, so I'll just move it over there. Yeah. Okay? Okay, so now, so this is basically, so you're going to encounter that when you have a bunch of particles and they're going to interact with each other, how do you find the net force on particular particle? Then you'll have to, first of all, draw it on the x and y plane to see how many forces acting on the particle, and do a vector sum. After you lay out this, and then you have to figure out each individual expression, F12, what is the expression for F12, F13, and F14, and then some of the vector needs to be resolved into x and y components. And then after you have all the x and y component, then your F1 net will be whatever the x component, you add them together from all these vectors, and then I hat. And then add up all the y components and call that, and that attach the direction, that's j hat. So that's basically how you would do it. Okay? So what about the magnitude? If I want to ask you what is the net force acting on particle 1? So this is in unit vector notation. What about magnitude angle notation? So in that case, what will be this magnitude if you have x and y component? Isn't that from chapter 3? Yes? Yeah. So you have the s component square and then y component square, right? And then to calculate, to find the angle, you don't just use the y component over the s component. What you want to do is that draw this vector onto, on your x and y axis to see which quadrant it is pointing. For example, if it's pointing this, then you can define your angle theta, and then so your angle theta, so that will be the opposite. So tangent theta will be opposite over the adjacent. And when you do that, make sure that you drop the negative sign. So you just have the theta. So, and then if you want to answer the question with respect to the positive x-axis, then you just use 180 minus that theta. That will give you the answer. So it really depends on where the vector is pointing. This is just a refresher from chapter 3. Okay? Any questions so far? So as you can see, what I just meant was that, what you learned from chapter 3, you're going to use it again because you're dealing with the vector, the forces. You have to know how to resolve the vector, how to sum up the vectors, how to use Pythagorean theorem, how to use the tangent theta, and so forth. Okay. All right. So we mentioned that gravitational acceleration and the free fall acceleration, they are not exactly identical. So the differences comes from the fact that our Earth is actually not uniform and it's also rotating. It's not actually just stay there. It actually rotates about its own axis. So because of its own rotation, so there is a rotational acceleration that's involved. When that's involved, it just means that you have to correct the rotation rate into account. So, for example, let's say this is the Earth. Okay, so you can treat the Earth as if all the masses were concentrated at the center of the Earth, and this is, let's say, an object. How many forces acting on this particle? How many forces? If it's lying on the ground, on the surface of the Earth, yes. Two? Wouldn't it be three? What other three?
I think there'd be force of gravity and then a normal force and then friction.
And then friction, so that's a frictionless. If that's frictionless, then that will be 2, right? Okay. So that's a normal force. What is the direction of normal force? That's upward. Okay, so the free body diagram, you have an upward normal force, and then there's gravity. So you have, let's say, Fg, right? Okay. So this is the case that you've done before that. Okay, you have a particle on the surface of the Earth. You experience 2 forces. One is upward normal force, and one is gravity. But then this whole thing is also rotating. Remember, your Earth is rotating. So there's a centripetal acceleration involved, right? So that the net force acting on this particle will give rise to the centripetal acceleration. So based on that, and the centripetal acceleration is basically pointing downward, if you remember your centripetal acceleration, right, in the radial case. So in other words, the net force acting on this particle should be equal to m and then times ag. Okay, I mean, that will be the gravitational that will be the gravitational acceleration, and this is the net force acting on the particle, and that just gives you the mag. So in that case, the force acting on this particle will have, if we take the upward to be positive, you have normal force minus mg minus mag instead of mg, because in the past we just used g, but then now it's ag. Okay, and that's equal to, what is it equal to? You're not doing it. I'm sorry. I think let's say, let me just, Fg, the gravitational force is this. Okay, and the net force is equal to m minus the gravitational force, right? So m minus mag, and that should be equal to the centripetal acceleration because it is rotating like this, which means I experience the inward or the towards center centripetal acceleration. What is the major centripetal acceleration? The acceleration, centripetal acceleration, that is equal to the magnitude v squared over r, right? So you have v squared over r, okay? And then because the net force is m minus, so we take the positive to be upward, so this downward, they differ by a sign. So you have negative mass times acceleration, and that acceleration is v squared over r. Any questions so far? So this is the net force acting on the particle that gives rise to the centripetal acceleration. So you have net force that is equal to ma by Newton's second law, and because the acceleration, the centripetal acceleration is toward the center, so And then this, this is, defined as positive because your n is upward, right? So they differ by negative sign, so you have that. Okay, so what do we have here is that our n here, the capital N, is what we call the free fall that's related to the weight. What is the force to prevent the thing from falling down? So that's equal to mg. That's our g here, okay, that you're familiar with, which we, in the past, we just said that ag is equal to g, but it's not that, and then you have minus this, and then you have this. So the mass of the object is actually irrelevant. It just get cancelled. What we have here is that you have your g, and then minus ag, that's equal to negative v squared over r. So v squared, so if you remember, for something that's rotating, your v and omega, they're related to each other. How are they related to each other? V omega. Yes, right? So you have v squared over r. We can just do this. And what we have here is omega squared times r. So on the right-hand side, you have omega squared times r. And then, so what we have here is that your g value, free fall acceleration, and, is it blocking you guys? Okay, I think, okay. So we move this to this side, and you have ag minus omega, and that, okay? So it basically just tells you that this free fall acceleration and the gravitational acceleration, they differ by this. And that comes from the fact that because the Earth is actually a rotating body. When it's a rotating body, then there's a non-zero angular velocity that you have to take into account. But most of the time, we just say that they are roughly equal to each other. Okay? All right, so that just gives you some ideas about the differences and similarities. And because after you punch in the calculator, your omega, what is your omega of the Earth? How do we find omega? The rotational rate of the Earth is, how do you calculate omega? No. You don't even have to go through that, complicated. It's not that complicated. The Earth repeats its motion every 24 hours. So you have the periods. Omega and period, they are related to each other, right? Yeah, so period and omega, they are related by each other like this, right? So if you have 24 hours converted to seconds, then you can calculate your omega because they are related to each other. So you'll find that your omega, and then after you multiply that r, actually is a very small number. So that's why you can use that approximation. Okay? All right.